Are we, can you guys hear me? Is this on? No. What do you do? What do I do to turn it on? Button. Now can you hear me? Kevin?
The light is green.
Now?
Yes.
Ah, okay. No, it's okay.
Does that one work?
I think it's okay.
Okay, go ahead.
Thanks, Kevin.
There we go.
Okay. So I am really, really happy to be introducing our friend and neighbor, Dr. Stanley Jordan, who's going to speak to us today on a title somewhat different to what is on the screen, but he will tell us what he's talking about. You said something about human immune responses, and what was the end part of it? I don't know. Never mind. Dr. Jordan is the Director of Nephrology and Transplant Immunology and Medical Director of the at Cedars-Sinai Medical Center in Los Angeles. And he is also a distinguished professor of pediatrics and medicine in the David Geffen School of Medicine at UCLA. And he got his undergraduate and medical degrees from the University of North Carolina, Chapel Hill. We have other Southerners here in the group. Hi, Rosie. And then he had a pediatric internship and residency at the University of California, Los Angeles, or UCLA. He had 3 fellowships at UCLA, and then he had a 3rd fellowship at in dialysis and transplantation at Children's Hospital LA. And he's board certified in everything you could possibly imagine. And I'm actually not going to read the rest of this wonderful bio that Stan gave me because, boy, somebody's doing their nails. We can see you doing your nails. He has a paragraph of all the prizes that he has won, which is longer than all the rest of the stuff that he's got on this bio. So I will just tell you that Stan has won many, many prizes in these fields of that he works in. And since the pandemic, he's been looking specifically at things about COVID. We used to meet him on our pandemic walks, and he would tell us his latest thing that he was finding out about COVID. And so that's what he's going to talk to us about today. So thank you.
Well, good morning, everybody. And I think I'll be able to take my glasses off here. And no nail filing during the talk, please. Okay. Okay. Thank you very much. So what I want to do today is talk about, I think most people, all of us really, have been overtaken by this pandemic, which is enduring in many different ways. And what I wanted to try to share with you is my personal journey with this, something that I really didn't know anything about. I'm a nephrologist, mostly, and an immunologist, looking at rejection processes in kidney transplantation and other organs at Cedars-Sinai for my career. But one of the things that really came up, and you'll see as we go through it, that I'm getting some vibration back here, Kevin. Can you guys hear me if I talk loud like this? Oh, okay. Okay. Yeah. I'll get close to me. Okay. Anyway, what I wanted to share with you is my own personal journey with this in terms of just the necessity of this pandemic. When in the 2020 we were overwhelmed with people in the hospital who were dying very rapidly, were very sick, and there was nothing. We didn't know anything about this. And we had to get to work to try to figure out how we could attack this terrible disease. And so take you through that journey. This is clearly the most intensely studied virus in the history of the world. But I think that you'll see that the advancements that have been made in understanding the virus and how it replicates, as well as developing defenses against it, will really have long-term benefits for our lives and for probably generations on vaccine development and, and specific therapies to prevent it. And from my standpoint as an immunologist, I feel like the most important thing is to prevent the disease. There are a lot of drugs you can take to kill it once it's there, but it's always better. My dad used to tell me he was in the Army Air Corps in World War II and Iwo Jima and those places. And he said, it's always better to fix an airplane on the ground. So if we can prevent something, it's better than trying to fix it. Okay, well, what about this virus? Well, the first thing that we noticed, I think I can almost talk loud enough. Can you hear me? This is really, oh, okay, I gotcha. Okay, good. Okay, so one of the things that we learned about this epidemic was that it's very similar to the 1918 influenza epidemic. And these are pictures from that time. Of course, no one knew what the hell this was. You know, people were dying. This was called the Spanish flu. I think we know now that people don't like to name it after a place because it implicates that these people started it. But the 1918 flu, or the Spanish influenza, really spread to the United States when the doughboys came home from World War I, the Great War, and on these Liberty ships packed in there, and they got to New Jersey, ports around the US, got off, and they all started dying like crazy. And they looked like this. People, we call this heliotrope cyanosis. See, their mouth is blue, their lungs would fill up, and they would die really within hours. And the doctors at that time didn't know what the heck was going on, but they would take, we'll talk more about this, when they died, do autopsies, take pieces of their lung and put it in formaldehyde. Maybe sometime in the future, someone could figure this out. And we'll have something to say about that later too, but that was just where it was. And so in the United States, I think 1.5 million people died. I'm sure it's, we don't know, but the proportionally would be much, much higher than what we had with COVID so far. Worldwide, 50 to 100 million people died of Spanish influenza. So this is where we were. Now we know a little bit about this virus, began to learn about it because from previous work with the SARS-CoV2. So it's called SARS, or coronavirus 2 is what this was called. And this is a virus and has these little binding sites, which are called RBDs, or receptor binding domains, that recognize human ACE or angiotensin converting enzyme inhibitors. And this is a survival mechanism for this virus because these things are in our nose, they're in our brain, they're all over your body. They break down a hormone that causes blood pressure to go up and other things. And now we know they're probably responsible for taste and smell. So the virus would hook onto that with high avidity and then create a lot of inflammation in the body. And this is one thing that, this is where I got into this, because this cytokine you can see is like, boom, IL-6. This cytokine means cell mover in Greek. So it is a hormone that the immune cells use to become activated. And this virus was just causing copious amounts of this cytokine to be released in the body. And unfortunately, I mean, it's good to activate the immune system, both what we call innate and then adaptive, but it's also very damaging when produced in excessive quantities to the patient. So here, the immune response to the virus causes a lot of damage and death in patients. So I've been working with interleukin-6 most of my adult life in terms of inflammation and autoimmunity. So we said, let's see what we've got. And we'll talk about that in a moment. So two principles we'll talk about today, and I don't want to get overly technical. And I use these papers and some of the references just to bring up points, I think, of steps and progress in our understanding. If you look at the immunity to SARS-CoV2, initially there are these, what we call innate immune system. And we'll go back here. This is like with complement activation and the cytokine release, just by your body recognizing foreign things. And they have these molecules in our bodies, and some of the cells called natural killer cells have receptors that recognize non-self, more commonly bacterial or viral-like epitopes or proteins that ancestrally have been damaging to bodies. So they go, boom, kill that. But then we have what we call the adaptive immune system, where the immune cells recognize these foreign proteins from the virus and make a cognitive blocker, an antibody or a T cell. So these, we'll talk about how this happens, but this is what is important. You have the T cells and the B cells. The B cells make antibodies, the T cells kill infected cells. That's pretty much what we have to know here. And so we're going to talk more about how this has evolved and talk about how we have to chase this virus with these variants and try to understand what's going on there, because this has become our biggest problem even today. So this is sort of one of the first papers that came out in the literature, just looking at sort of reiterating what the immune, I don't know if I can show you, yes, here we go, good. That how body responds to an immune challenge. And these are the adaptive immune responses. So initially you can see that there is antibody responses. Then we get memory B cells, and then these we have IgG, immunoglobulin G, immunoglobulin A, and then IgG is really the most effective, and again, is the most refined response to a virus or an infection, and it goes away over time. And then it can come back if you see it again. The T cells do the same thing. But nobody really, I mean, this is sort of like the art the years ago where they had New York City and then the rest of the country with little things out there. Yes. Okay, yeah, sure, I'll do it. I'm sorry about that. Huh? Okay, good, yeah, thank you. So, so you have this memory aspect here, and you have all this acute phase, but you can see there's these little dips here where people don't seem to have anything. So we're going to talk about that. So one of the things we did in our lab is try to understand the human immune response to this virus. And this shows you some of the, how this really works. And so when we have people that get infected, we know it's in the nose and the throat. These are viral particles binding to these ACE2 receptors. Then your immune system gets to work. These are called dendritic cells. These are cells that go out and grab little, with their tentacles, grab pieces of this virus, digest it, and then sort of array it on the surface so that these cells, the CD4 T cells and the CD8 T cells, can see it. So why is the difference? Well, the CD4 cells are what we call canonical T cells, like the Pope or something like that. You know, they process it first and then they instruct everybody else in the immune pathway. So these cells prime B cells to make antibody. And we know that these cytokines, when they're activated, interleukin-2 and then tumor necrosis factor alpha are produced as prime cytokines or canonical cytokines. The CD8 cells, on the other hand, are going after just killing the cells. Once they see virus, they kill the infected cells. And that way you have a cellular component and then an antibody component that is 1-2 punch to get rid of this stuff. So they make a TNF and gamma interferon. So we'll get back to this in a moment, but this is how we understand the immune response, at least at a cellular level. Now, how do we determine this to COVID? Well, this is where it got sort of exciting for us, because we developed some assays in our lab at Cedars to look at human immunity to COVID-19. And in the early days, we were looking at, and I'll show you something in a moment about this, but where we develop a test where we just take over here 3 cc's of blood, you know, less than a teaspoon, and we can expose it to these little particles. These are peptides from the virus, and these are spike, which everybody hears about the spike. Those are where vaccines are made, but there are many others. And at that time, we didn't have any vaccine, so we were looking at immune responses to the virus itself. And down here, I won't bore you with this, but these are both CD4, and we were very excited about this, CD4 and CD8 responses in infected people. You can see most of it's spike that they really get after, but there are multiple other, like nucleocapsid, open reading frame, and membrane proteins that would sort of be like a belly shot to the virus instead of just going after this binding site. But the spike is a prime thing in infections. And we could identify this by looking at cells, the CD4 cells, we can sort CD4 cells in a flow cytometer and then look at these cytokines, TNF, IL-2, TNF, gamma interferon, and CD8. And we can say how many of these cells are responding to this. So this was pretty exciting because we could determine immune responses to these viruses. And then we looked at it in terms of vaccination. If we looked at this, or excuse me, with variants at first, we got the variants. The early ones were epsilon, and then there was a delta, which was a big problem. But you can see here what we saw, that in that people who had immunity to the ancestral, we used to call it Wuhan, now we can't because of Spanish flu, Wuhan, and so now we call it ancestral spike, had immunity to these variants. So it was very encouraging that these had not gotten away from the ancestral exposure, that the immunity was conserved. So it would give you good immunity to that. And then the vaccines came along. And this was really fun for me because we were doing this back in 2020, November, December. And two of our infectious disease people came to me and said, you know, we're scared to death. We're working with these patients with pneumonia. There are a lot of people getting sick in the ICU, and we just don't know. We are participating in the UCLA Pfizer vaccine trial. It had not been released at that time. And there was no antibody test at that time either. The test that was looked at was for membrane, which is not a vaccine, but to see somebody had the virus. That was it. So what we did is, we just took their cells and we exposed them to spike proteins. And indeed, you can see right here, these little dots in here, these are about 1% of the circulating T cells were specific for SARS-CoV2 spike. I said, I think you got the vaccine, but we didn't know. I think you're okay, because it was placebo controlled, but they found out 2 months later that indeed they had gotten the vaccine. And one of the doctor's sons had got the AstraZeneca vaccine, and he said he had a really bad sore arm and he felt, you know, and we did his T cells, we didn't see. And she said he was in the placebo. So this is kind of funny. I tell you about these side effects. Sometimes people, you know, they can conjure them up. So anyway, you have to be, this tells the truth. You have exposure or you don't. So this is one of our first papers, and I won't bore you with that, but basically, again, we found that the immune responses to all these variants up to the Delta was the same. And these are people right here that were infected, and these are vaccines. So it looks pretty good, doesn't it, for both CD4 and CD8. So we were pleased with that. And I think it gave us a feeling that we could really be helpful looking at this. This is, I don't know if you guys, you probably don't know this. This stuff over here is called RNA sequencing. And this was done by these really great gals at Cedars in ID, where they looked at about 1,017 patients that were in a hospital infected with the virus. Now, just to tell you how bad it was in the early days, about 30–40% died before this. And so we were concerned about that. However, the thing that is, I think, interesting is that this was, we looked here at the epsilon variant, and looking at the genes were upregulated. And what we found was that indeed the virus was more infective. But when you looked at the T cells had adapted to knock it out. So it wasn't pathologic, as pathologic. So having those T cells, even though they were not Delta or Omicron, or excuse me, epsilon, all the Greek stuff, you still got pretty good immune response to that. So, so this was fun work to do. And then this is same thing here. One of the things, though, that we did last year is we looked at this with Omicron, and at the end of the year, and we have about 30 of our nurses and some docs that we've been monitoring over time, and they had 2 vaccines of the, or no, 3 vaccines, excuse me, at Cedars of the BTN 282 or BTN 162b2, which is the Pfizer vaccine, in healthy people. And so we looked at Omicron. That was a new one. And we're not seeing too much good stuff here, right? Look at the CD4, CD8. Now, this was more than a year ago. So when we looked at that, we go, this doesn't look good. It looks like people that the current vaccines are not giving immunity to the virus, Omicron virus. And look, sure, please, yeah.
The line represents the average.
Yes, yes.
So those horizontal lines, group of dots, that's the average. But especially if you look over on that right one,
Pretty bad.
it's very near zero.
So yeah, these, right, you're exactly, thanks for pointing that. And you can see it's significant too. So significant means there's significant difference in these responses. And for the CD8 responses, we would anticipate that you would not have good killing of virally infected cells based on what we know about how they work. And the CD4 cells are also very low. A lot of people below the line, and these are healthy people. So this is even worse. But this is telling a story for us too, because one of the things mean and plus minus standard deviations. So these are the, and this is an important thing too, when we look at the antibody responses, we look at neutralizing antibody, and neutralizing antibody to SARS-CoV2 is sort of the moniker that we use. If it, and why? So what we're doing here is looking at the ability to block viral ACE binding of the virus to ACE. So if an antibody does that, it will have the ability to render what we call sterilizing immunity. So it will prevent infection, and if you have high enough antibody, it will clear it very quickly. However, this is not good. So we knew it was going to be a problem. And others have published this too, that even in normal people, that the Omicron was going to become a very infectious problem. So, and we know that it did. However, right, we know that it's not as bad as the ancestral in terms of disease. And we'll talk a little bit about that as we go along here. So this is some data we've also done at Cedars with Susan Ching, who's just an amazing person. She came from Brigham at Harvard and is a cardiologist, epidemiologist, has put together through a large NIH grant called Corral study, or we call it, we enter patients in Cedars, we enter patients and staff into these studies. So we can get about 4,000, 5,000 people to study for just general ideas about immune responses to SARS-CoV-2 vaccines. And one of the things that this paper that we were involved with looked at, and at Cedars, we all use the Pfizer vaccine there, and people got it, is if you look at this immune response time here, this is minus, these are antibodies minus. Of course, some people over here already had the virus, it looks like, infection. And then you can see that if you never got infection, this is your immune response to the revaccination. But if you had been infected, you get a good boost out of that because you already have pre-existing memory T cells, memory cells. So those are very, very important. The memory, we'll get to that in a moment, is a component of the immune system, which is very, very interesting and critical to our survival. And this being able to boost it, if you've had a previous infection, it's okay to get a vaccine because you get a real boost out of it for antibodies that last a long time. And we also did this work with Susan and Peter Ching, looking at more involvement of the T cells. And here, a lot of things sort of pop out at us. You can see that most people, when they're vaccinated, like the controls over here, that you make a lot of antibody, you get a lot of memory B cells and T cells. But there was a subgroup here who didn't. a number of patients who just, for reasons we don't know, did not respond to the vaccines. And again, this is important information from a personal medicine situation, because if you're not responding, why are you not responding? Of course, one of the things we do, we make people not respond. We put them on immunosuppressive drugs. So people that have been on immunosuppressive drugs often do not respond well to vaccinations. And we learn more about it with this virus than anything else. In the past, we just give vaccines. The vaccines, you're done. Probably they didn't work that well. And so with this virus, we know that a lot of people don't respond. However, these are supposedly sort of normal people. Why would that happen? Well, we know that the immune system, when I showed you those dendritic cells over there, sort of arraying the antigens, the T cells recognize it in context of binding to what we call DR molecules, HLA-DR, and then picking that antigen and getting a signal. Some people's constitution of their, what we call histocompatibility complex, doesn't recognize the virus. Now, if we all had that, we wouldn't be here today. We'd all be dead. But nature has allowed us all to have the greatest diversity in this MHC molecule on our immune cells. So an enormous amount of diversity. So you have a lot of, at least most people respond. Some people may be low, some may be high, maybe that's enough. But if you don't respond at all, or have these insignificant responses, you're at high risk. And so we'll talk a little bit about that in a moment. So this is, valuable information, I think, here. And so getting into that, this is a paper one of my colleagues, Dr. Heger, who's now at Cedars, did in Science Immunology, I think, where he talked about how do we deal with this issue where people are not responding to vaccinations. And I think this really puts my feeling in this is about all my experience with this, is while antibody levels are emerging as correlates of protection in healthy subjects, there is still an urgent need to understand the relative contribution of humoral, which is antibody, and T-cell immunity in conferring protection. So that's what we have been aiming to do, because it's different. And you'll see that it's different. And I think that we can't just look at antibodies. And one of the things that came out early on, there was a paper from UCLA about before vaccines, where people had COVID and they followed their antibody and they go away and they go, oh my God, the sky is falling. Everybody will be reinfected and die. You don't get good immunity. There's no vaccine. So, but it's just not true. And we'll talk about that in a moment. So one of the things here, this is another study we just finished looking at the same sort of thing. And this is something, all this stuff came up, and I think we'll all of us here in this room, or almost most, you guys don't have to worry about it, but back there, is that people say, well, if you're an old person, you're not going to respond very well. It's not true. Females respond better than males. Not true. So it's like, if you look at this data of more than 4,000 people analyzed over time, it looks like all these things are just not true, that we all have the capacity to respond. There may be other issues that would modify that, like our immune status. So getting vaccines or being worried about it because you're older, really, if you're getting your vaccines, you should have pretty good responses. And except for this, they're picking on me here. Look at this. Big difference. Solid organ transplant recipients. So here we've identified a group of people who are at very high risk for not making antibody and having poor immune responses to COVID. Okay. And this is a paper we did last year too, where we looked at this, were T cells, and basically see the same thing. Pretty much, you do see more T cell responses in transplant patients, but you're nothing like controls, both for CD4 and CD8. And if someone would go to the next one here, and this sort of sums it up down here. If we look at the T cell responses in healthy controls that have been vaccinated, 88% respond. And this would be, and this is also for spike IgG. This is the antibody titer, 93%. So the vaccines are pretty good. But look for this here. Only 50% of transplant patients get a T cell response. And these are the different types of treatments we use. Here, 33% had antibody. And with this is our most common transplant immunosuppression, tacrolimus, 50 T cell, 10% antibody. So they're very, very susceptible to infection. Because if we step back, if you look at the antibody titers, if you don't have them, I think I have some slides on this later, but antibody is critical to prevent infection, sterilizing immunity. That's the word we use. So if you have antibodies, you will be protected. But if they're not there, you will get an infection. Now, people thought that, oh, the sky is falling because there's no antibody. However, 50% have T cells. What's the difference? Well, the T cells are there. They're memory T cells that are at the ready when that first wave of defense, the antibodies, fail to interact with that. So to interact with the antigen. So you have to be infected, but once they spread out, they're going to kill those cells. So you get a muted infection, more likely than not. So having T cells is important. And this is something that we found out with this assay along the way too, is in our transplant patients and other patients. There were several patients in here that had malignancies, lymphomas that have been treated with B cell depleting drugs. So the B cells, remember, make the antibody. And they had no antibody. And people were coming, Orange County, all over the place. I don't have antibodies. What do I do? And so we looked at their T cell. This guy here, you can see that he had a vaccine here, and he had tons of T cells. But his doctor down in Orange County gave him another booster because he didn't have antibodies. And I said, every T cell in your body is going to be focused on COVID. I think you're okay. You don't need to worry about it. You got an army. So these people who are not on other immunosuppressives really have a divergent immunity. They don't get B cells, but they have an army of T cells that really come after this. So it's very interesting how the body adjusts to compensate for the B cell or antibody depletion. And then the other thing that is important here, just to talk about it for a moment, is that unlike that early slide I showed you with the mountains and stuff, the little New York versus the rest of the world, what has been found in people who have COVID infections, that they get very broad, strong memory, CD4, CD8 cells, and that it's and that they have not just memory to spike, but they have memory to all these other proteins. And these proteins are going to protect you in many different ways from infection. So that's, again, a little bit better situation than the vaccine, where we just have the spike. So sometimes maybe having the infection, if you have a mild infection, and I'm in a study at Cedars where we looked at that, and I think August I got a very mild case of COVID, and they looked at my antibody to spike for the ancestral spike and then to Omicron, and it was spike for ancestral, good, no Omicron, and it was about 5,000 units. Oh, thank you. Thank you. Yeah. I was hoping for some vodka, but it's a little bit early. But anyway, afterwards it went to the infection a month later. It was 41,000 units per mil for antibody, and the T cells had picked up the Omicron and the antibody Omicron. So it was really fun to see how you can really figure this stuff out. So I want to talk about this because, and I said our salvation are B memory cells. And I think you'll see when we get through this that there's some really interesting data, not only for COVID, but for other viruses that have helped us here. And this is a paper that was done by Shane Crotty down at Scripps or at the La Jolla Immunologic Institute early on, showing that these B memory cells, we showed that earlier, they're the ones that could recall antibody. They don't have a half-life. They just keep going. All others, antibody and T cells, sort of go away pretty quickly, but these things stick around for a while. Well, how long? How long? This paper is from Journal of Immunology a few years ago, and I think most of us in this room had probably smallpox vaccines as a child. You go, well, how long does that immunity last? Well, Shane showed that he could get T cells or B cells here, B memory cells, 60 years later, still there. So people say, I should get another smallpox vaccine. No, you don't need it. It lasts a lifetime. These cells are protecting you for the life of your body. How that works is really interesting. I don't think we could expect anything in today's world to last 60 years, right? So, but your B memory cells do. And this is one of the most fascinating stories of medical sleuthdom, I think, that there is. And going back again to the 1918 flu epidemic, we know thousands and thousands of people died, and there was no, what is it? They don't know what it was. And so they had put, sections of lung tissue into formaldehyde and if you have ever a chance, any of you have a chance to go to the Armed Forces Institute of Pathology at Walter Reed Hospital. And I was back there a few years ago and they took me on a tour there. It's fascinating just how the medical issues that have been afflicted the US Army and the military over the years. But they had these bottles of these little pieces of lung from these poor guys from 1918. And there was a scientist at NIH, he says, maybe we go back because nobody knows what that virus was, right? Nobody knew. So we looked at it, or they looked at it, and they tried to sequence it, and they go, we can't get enough sequence out of this tissue. We know there's a little bit of DNA there. We can't do it. And then a paper that was in Science said, perhaps if there was some way that bodies were preserved, that of people who had died in this epidemic, that we might be able to isolate it from their tissues. And this guy, Peter Halton, and this is a book called Flu. You love this book. It's a great book. He is a pathologist at the University of Colorado, and he read this and he goes, well, my wife and I were missionaries, are missionaries. We go to the Inuit tribes in Alaska, and there are big, massive graves there from people who died in the 1918 flu epidemic. And so he got permission and he was able to exhume. You can see here, this lady's chest is open, pretty well preserved. He took the piece of lung tissue from her in the permafrost. That's why they're frozen, they're in the permafrost. And they isolated the 1918 flu virus, live virus. Now people say, what the hell you're doing? I couldn't remember. I don't think the poor guy has a mask on. He could have started this thing all over again. And people were really concerned about it. But this is H1N1. We see those today, but they were able to sequence the H1N1 genes, hemolysin and neuraminidase, and identify this virus as of the 1918. And this was in 1990s, about 2000, 2001. So he figured it out, and just by going back to the permafrost and getting this poor lady's grave up and do it. But then it's sort of interesting because this paper came out in 2008, and it's one of the most fascinating papers. It was in Nature. And these guys identified 32 people who were alive in 1915. And came in, they gave their blood, they're 90 years old now, right? And they were able to show that in 7 of them, I think, that they had antibodies to this viral peptides, which this guy had isolated from the graves of these people. And the B cells in their body, the memory B cells, when they made monoclonal antibodies out of them, would protect mice from the H1N1 virus. So my feeling is, that's probably why they're 100 years old, that their immune system is sticking around like that. But it's very fascinating at how long these cells last in your body. So we don't know about COVID, but some, we do have to revaccinate, but still, we all may be protected for long periods of time by these memory B cells. And this just shows you that the neutralizing antibodies do go away after a vaccination pretty quickly, but we shouldn't be too concerned about that. That's something that we know that those banks of memory are there to come back and help us. So, and this is one of the, I really love this paper. It was also in Nature, I think Immunology. It's called T Cells to COVID-19 United in Diversity. Maybe we should take a lesson from that, right? From a sociologic standpoint, but looking at how these T cells develop both CD4, even to minimal infection, and then to, and again, this was before vaccines and more severe infections, the half-life really tends to be pretty good and it should be reactivatable. So with this, we know that our body responds in a way to try to give a very collective immune response, both antibody and then T cells. But the T cells are very important. And we can't look at the antibody alone. Somebody says, your antibodies are gone, you don't have immunity. You tell them, no. Dr. Jordan said not, and other people do too. So we have T cells and B cells.
You're talking about the sociological aspect of it. One thing that this paper that you're talking about here, the paper,
Yeah.
show there are some people that simply can't get to the immunity.
Yeah.
But that means that the rest of us have a moral obligation to do everything we can to maximize our immunity to protect those.
Thank you. That was my next slide. Here it is. Personal responsibility, shared responsibilities. It should be a mantra, right? We have shared responsibilities in our society to protect those people who don't have the ability to protect themselves from an immune situation. So this is a Swiss cheese and a lot of holes in it, right? So vaccines certainly are our best defense. I think we know that. And so we'll talk a little bit about that. I want to talk about this too, because I think this book really reminds me of our situation. But in the 1950s, the last best hope. And for me, this is a polio hospital in Asheville, North Carolina. I was in this hospital for 4 months. And I remember seeing these little kids on the Iron Line. They wouldn't be there the next day. And these massive infections and crippling diseases that came from this was such a scourge. And I think most of us remember that in some way. And that there was no answer to this. Same thing. Thanks to President Franklin Roosevelt, not the NIH, but at the time, but the March of Dimes, you remember that? They developed a vaccine, Dr. Jonas Salk. And I love this paper. This is on my birthday in 1955. I'd already had polio in 52. Salk polio vaccine proves success. Millions will be immunized soon. City schools begin shots April 25th. Efficacy 80–90% and an advance in 1955, right? So I was looking at this. I mean, this is about as good as we have with the vaccines today, but with a lot more noise. So of course, people lined up for this. And they lined up because it was such a scourge. And this book, if you haven't read it, is really good, called Patenting the Sun. And it comes from an interview that Dr. Salk gave to Edward R. Murrow. I remember this guy back in, he was always smoking like a Chesterfield or something. And but he asked Dr. Salk, are you going to patent this? He goes, how can you patent the sun? How can you patent something that will bring so much life and relief to people? We don't see too much of that anymore. But I really respected this guy. And I had a chance to meet him when I was at Scripps Clinic and talk to him briefly. And it was quite an honor that just considering the things that he had done and how he had helped so many people with his work. He wore an ascot at that time and he was married to Picasso's widow. So he did okay, even though he didn't patent the polio vaccines. But what a guy. I think that, but this is a good read. You see these kids with it's just, you know, it's different because this was the data on the vaccine for COVID, the first paper in like December 2020. really protected, but it wasn't at, yes. Oh, yes, this book. It's not about the polio. It's just the way I look at vaccines. Like at that Swiss cheese, we're out to the last slab. You know, we're on the 1 yard line. And we have to get it in. So I think that this is an older novel. I can't, you know, I read it several years ago, but it was not about the vaccines. So, but I think that the novel on patenting the sun and also the virus by Gina Colada are very good books to read. Like, so we validate the vaccines. We know that they were good there. And I just want to close by talking about what, yes, I'm sorry. Yeah. Of course it is. They're all there. It's all there. They're just waiting for us to let down our guard. And we do see cases of polio now. There have been cases of polio in the United States, outbreaks around the world. It had almost been eradicated, but in like Pakistan, Afghanistan, they don't allow children to be vaccinated. And so you still see those problems. And in the United States. And I think we see all of us, and I don't know what everybody's personal views are, but I think that the point I want to make is that the anti-vaxxer movement is certainly a new thing. It wasn't what happened in the 50s, where everybody was so happy to see something to help people out. And I think that in my own practice, you know, we have patients, these transplant patients who don't want to get vaccinated. They hate it. And I had, and I'd always talk to them, and I get these little reviews of my performance with patients, and I had 8 10s, which is good, and 2 0s. Yes, I'm a pro-vaxxer. That was it. So, but I think that you're, you know, and again, it goes back to the gentleman said, what are our shared responsibilities in the world? How bad you would feel if your negligence causes somebody else to get sick. Not everybody looks at things that way, I guess. So I think this is probably one of the most important messages from my standpoint with this work. So again, the advances, and I'm going to close with this. We can take some questions, I guess. Yeah. Okay, good. Are we always going to be chasing the next variant around? You got to get, you know, are we going to be pin cushions for these vaccines? That does not hold a lot of desirability. So I saw this lady, well, let's go back. Again, just, this is another about 4,000, this is one of the new papers we're doing. Looking at the middle thing here, one is odds ratio going reduction for infection, on the right would, you know, would increase infection risk in patients, reinfection after vaccine. So it's a very important piece of information, I think. And see, most of the things that you're, look at age, males, females, all this stuff, obesity, a little bit of a risk. All those other things, heart disease, not much, that sort of thing. But if you look down here, this is the story. With each vaccine you get, you have a much higher ability to protect yourself from the infection. And that doesn't count the bivalent vaccine right now, which we have. So this is data done with just the 3 vaccines. And this is, you know, about 4,000 people at Cedars with different risk. But if you look here, again, they're picking on me. Immunosuppressed patients, and also getting, at his point, you know, the shared responsibility here. If people can't make an immune response, how do we deal with that? Well, there's a couple of things here. This is the vaccine development this is one of the most exciting things I've seen. I was in Chicago last April. It was actually snowing first week, and at Association of American Physicians meeting. And this lady, Pamela Borkman, who is one of our Angelinos here, she's at Caltech. brilliant, brilliant lady who has developed a new vaccine strategy, not using mRNA, because that was one of the problems with the current vaccines. People, you're messing with my genes, it's going to cause different problems. But this is a peptide vaccine, so it's protein, more traditional, but very refined proteins. And she has these, what we call mosaic 8, where they can put like 8 different peptides on these little microspheres and use them as a vaccine. And what she did is look at proteins that are on SARS-CoV2, SARS-CoV1, and then she identified on this receptor binding, or not on the receptor binding domain, but spike, a region that does not mutate, that is not recombining at a high rate. This is where our problem is. Up at the receptor binding, all this stuff is going on. The antibodies don't work anymore. So she made the peptide construct to that. She initially immunized with all 8 and got protection. These are in mice. And then she immunized with just the 1. And it gave protection against all coronaviruses she tested. Neutralization antibodies. But the potatoes hit the road here with this. They had a primate model where they vaccinated with the one non-recombinating protein or placebo. About a month later, they intubated these animals and poured SARS-CoV2 or SARS-CoV1, from many years ago, 17, 18 years ago. And you can see here that on day 2, this is BAL, or this is the lung fluid. You can't get any virus out of these vaccinated ones, but look at the ones that weren't vaccinated. The non-vaccinated animals died within 3 days. The others were fine. That's a pretty good test, I think, of this therapy. But more importantly, it also negated SARS-CoV1. So these may be the next vaccines that would give us long-term immunity to multiple coronavirus. It may solve this problem. And good on her, right? She's doing great work over at Caltech. So the last thing here is, and I shared responsibility, right? We have to talk about that. How do we compensate for vaccine failures and immunocompromised patients? Well, there's a couple of things. I say here, with the help of 10,000 of your friends, we can do it. And the reason I say that, these are people who are plasma donors and people who have been exposed to COVID vaccine or through infection can donate plasma. Now, one plasma unit is going to be variable, but with a product called IVIG, immune globulin, that was given to people who are immune deficient, you get the united force of 10,000 people or more in one bottle, because the plasma from these people is purified and IgG selectively isolated, and it's in there. So we were interested in this, and I know it probably doesn't show up very well, but we looked in 2021, early 2021, at these IVIG products, and we didn't see any antibodies to COVID in them. And I was saying, why? It's been around for a year now, because they isolate about every 6 months. And then, but the end of 2021, early 2022, we started seeing, well, more early 2022, that there were a lot of antibodies to COVID in these IVIG products. And we ended up having to dilute it out about 1 to 1,000. And we can still see the protective effect. And this right here shows you these are patients, our transplant patients who had no antibody. They get 1 dose. Look at this. They're up here, but protected from this. So 10,000 of your friends who are sharing responsibility or giving plasma are helping these people do well. And we just recently looked at it again, and now we see Omicron neutralization in these products as well. So I think this is very helpful for those that are immune deficient. And this is about 300 patients, 321 patients who received a monoclonal that is out there called Evusheld. And it's for immunocompromised patients. It's 2 monoclonals that bind to our receptor binding domain that give passive immunity here. And you can see that the half-life of this stuff is really good. It's because these antibodies are genetically altered to give them a longer half-life in the body. This is out to 40 weeks almost. And see, they're not degrading like our natural antibodies would, which have a half-life of about 24 days. So this kind of technology is going to be very helpful too for those who need passive immunity. So this has been, and we looked at these patients, we saw more than a 50% reduction in risk for COVID infection and only 3 hospitalizations and no deaths. So there are many fronts: passive immunity, active immunity. Immunity is important for controlling this virus. So I'll stop there. Maybe we can take some questions. I just want to show you the guys that do the hard work here at our lab, doing these T cells and antibody testing, and good on them too, because they really do a great job. And this is, this is a crazy place. It's called Hardawara. This is the Ganges River. I was there a few years ago, and I got, not that I have a religious preference, but I got baptized by a Hindu priest here in the water, and it was really cold, but it was fun. It's a beautiful place. Very religious people get out there at night and sing, and and the guy told me, okay, let's put, you want to, they have a little chrysanthemum wreaths, and you can put a candle at night and put it in the river, and it's such a beautiful scene, all these floating down what they call the river of souls, and say a prayer for your family, for those departed. Same everywhere, right? Okay, thank you so much. Any questions? I'll be glad to take them. Yes. Yeah. Mm-hmm. Yeah, thanks, Kevin. Yeah. Yes, ma'am. Yeah. Well, what is the position on mask? Masks are good. I think, it's important. When we look at our transplant patients, we didn't see really high rates even before the Evusheld, because most of those guys are so ardently aware of their susceptibility to infections. So you can reduce the risk for infections by wearing masks and also isolating. But everybody I talk to, our patients, I'm just so tired of being at home. I want to go out to a restaurant. I want to see my grandkids. I want to go to Europe. One lady wants to go to Iceland. I go, well, go. You're vaccinated. You have antibodies. You have T cells. So get out of here. But those things it just becomes a burden after a while for people, and some people just become so almost just totally afraid, agoraphobia almost, to go out. So we try to want them to get their lives back. And providing them with these types of treatments really helps. But yeah, we have to. Yeah, you're right. I can tell you still today, we have to wear masks when we enter Cedars-Sinai. And we can't gather like this. But we're in a situation where there are a lot of immunocompromised patients. Yes, sir. Mhm. Yeah, okay. How do we deal with anti-vaxxers? It's a very tough thing. And my view has changed because I find that I would be on our video visits, and I would try to convince people. I would tell them how at risk they are and things of that sort. And they get pissed off at you. And, because it is their belief. And I respect that. Now, I just say, I want you to know, I said, have you been vaccinated? And I said, no. So do you understand the risk, and that if you have no immunity, you could die from the virus? And they do. So it's very, very interesting to me that even at the risk of their own lives, they would not get vaccinated. And it's just, I think it's more than just a personal choice. It's sort of a mantra that's been spread out there. And, a lot of people died because of it. Yes, ma'am. Oh, boy. Yeah. You're asking me some tough questions this morning, but what about people that have myocarditis, problems like that from vaccines? How do we deal with that? And that's a real issue. It does, it does happen with the viral infection. And this is the really next frontier for COVID research, is what we call the long haulers. We have so many of those patients. The retinue of that virus is well beyond the mortality it caused. And one of the things, getting back to what I talked about earlier, I don't know if I had those slides on this presentation, but we did look at IL-6 treatments in the early days of the pandemic at Cedars, when we saw in our lab that the IL-6 levels were very high in those people with acute pneumonia and all these other problems, and we treated them with a monoclonal called tocilizumab or Actemra, and it's an anti-IL-6. So you have a cytokine that's high, you have an antibody to it. We treated, and what we found, one of the first papers on this we published on this treatment, but we were actually able to reduce inflammation, reduce hospital stay, reduce ventilation, and save lives. Yeah. Thank you, Susan. I was getting to that. So, but we did see myocarditis. So anyway, but anyway, what reason I bring that up, I have a lady, or I have two patients now that had COVID and also vaccine and got severe myocarditis. And one lady came into the emergency room with what we call pericardial tamponade, where the fluid around her heart stopped the heart beating. And you have to stick a needle into the heart, drain the fluid off. And it just keeps coming. And we measured those IL-6 in those fluids, and we found it was exceedingly high. So, the first lady I treated, I treated her with the Actemra. She told me, I feel much better after the first infusion, and we completely corrected it. So it's a case of one, but we go forward with that. But this may be something that we would need to use these medicines that work very early in the pandemic to save the lives, to really treat some of these inflammatory sequelae of vaccines and or infection. And for the post-COVID things, now there's more data emerging to suggest that what we're probably seeing in many, many patients is that there is a residual infection in these patients. There was a paper in Nature, very well-respected science and medical journal, showing that in 44 autopsies performed on people that had severe COVID, they were able to isolate the virus from their brains. It was still there. So this is that every day we're learning more about this. So the question is the virus in these tissues? But we know we can help it by controlling the inflammation that this virus is causing. Ultimately, try to get rid of it. We think things like the immune globulin that I showed you with those high titers may also help get rid of the virus from the body. But those have to be tested, and there are studies that are just beginning, but nobody knows anything about this. Really, nothing at all, the post-COVID syndrome. Okay. Is that all right? Had enough?
Thank you very much.
Thank you. My pleasure. Thank you.
I have a couple of announcements.
Okay. Thank you. Sure.
So that was really great. I got a lot out of this. There are a couple of times I was a little bit like, I'm not sure I'm putting it all together, but one thing I really got out of it is, aren't we lucky that there are all these brilliant people working so hard on these things? How much worse off would we all be if we hadn't? And how much confidence we might have that, maybe we'll deal with other things that pop up in the future too, thanks to these people who do this work. And the two announcements. One is that we should all keep Barbara in our prayers. She's still convalescing from COVID and fighting it, really, still apparently. Yes. And Second, next week. Next week, Marilyn Anderson is going to lead us in a discussion of a fascinating book, which The Beauty of Dusk, and which has tells a story. It's autobiographical. It tells a story of a man who lost the sight in one eye and had his sight in his other eye threatened, and how it led him to some spiritual evolution that he felt was very beneficial, and he's sharing it with other people. So I think that'll be very interesting. Thanks everybody for turning out. This was really, really interesting. Thank you, Stan.
There is a book that's
Oh, yes. Let me give you this.
Okay, yeah. Many of you may know he wrote The Emperor of All Ailments or something like that. Maladies, yeah. And then also about cancer and one about the gene. He has now one about immunology called The Song of the Cell. So you might want to read that. It'll have a lot of this Siddhartha Mukherjee. He's on TV a lot. He writes these books, but I think he writes very well about some medical issues that help understand.
Thank you. Does anyone else have anything else to add or ask about? All right. Thanks again for coming. Take care. See you next week.